you know, we're talking about, we're trying to get strain rates. So remember how we derived strain? We looked at the, you know, ds squared minus ds squared, that whole thing. We did a bunch of manipulations. So basically we're going to start along those same lines. So we had, you know, just like before, we have d little s squared minus d big S squared. And we're going to take the time derivative of that, d dt. Well, yeah. Let me write out. So, of course, as we already looked, we had, you know, this is equal to, we already derived this, right? This is equal to 2e in terms of the Lagrange strain dx. And so, you know, if we want to take d dt of that, that's also equal to d dt. And again, all of these derivations we've already covered. You look back. All right. But remember what I said earlier? So, right, remember dx transpose dx is ds squared, right? Remember what I said earlier? Anytime you take a time derivative of anything with a big X in it, it's just going to be 0 because by definition, it's not time dependent. It's the reference configuration. So that term and that term are 0, or, you know, another way to say is we don't need to worry about them. So really all we have to do is take the time derivative of little ds squared, which that's equal to d dt d little x transpose dx that's equal to, again, reversing the order of operations on the derivative in the terms, that's equal to d partial x transpose dt dx plus, just using the chain rule, dx transpose d dx dt. Just going to change this to dx dt. Well, what do we say this is? This is the velocity. This is the velocity transpose. Right? So now we have dv transpose dx plus dx transpose dv. Well, dv is equal to, well, dv transpose is equal to L dx transpose dx plus dx transpose L dx. Then, you know, our rule with transposes, we can distribute the transpose by taking the transpose of the components and then swapping the order. So we have dx transpose L transpose dx plus dx transpose L dx. Then we can pull out dx transpose L transpose plus L dx. This is equal to 2 times d. And d, or d is equal to 1/2 LT plus L D is called the rate of deformation tensor. And if we looked at what the components of it are, or we wrote it down in component form, it's 1/2. Remember, L is partial V partial X plus partial Vj partial X. All right. And again, why the 2D? Well, it's the same thing. We want it to be consistent with the small strain rate, right? So we know the small strain tensor, basically the small strain is 1/2 partial Ui partial Xj plus partial Uj partial Xi. And then we take the time derivative. I'm just going to put a dot on that, a dot on the u's. Well, the time derivative of u is v, right? So 1/2 partial v I partial xj plus partial vj partial xi. Right? And so if you look at these two equations, this was derived completely with finite deformation quantities, right? This is the infinitesimal strain, and you see that essentially they're the same thing, except, again, this technically is in the current configuration with respect to little x. In an infinitesimal strain, there's no delineation, right? We write big X because that's our reference configuration, but in the small strain, that's all there is, right? It's one configuration. And so, again, because we have little x is equal to x plus u, right? And if u is small, then the two configurations coincide. Right? So again, that's where like the 2D comes from, to make it consistent with the small strain rate. Okay, so this is a rate of deformation tensor. It's a strain rate quantity in the current configuration. We'll look at in next class what the rate of green strain and the rate of Eulerian strain are, and we can derive them in terms of D. And then after that, when we go into stress, it'll become even more kind of relevant to why D is like a thermodynamically consistent strain rate. Basically, this tensor times the Cauchy stress gives you power, units of power, which is a thermodynamic principle, right? The time rate of change of work.